We'll hand you the weapon of your choice. Thank you.
Thank you. Thanks. And despite the Gaia green color of my t-shirt, if you look really closely, you see there is a Zenseact logo here. Yeah. I'm very excited to be here today and tell you guys about the exciting journey that we are on at Zenseact. And I will proudly present a lot of results and examples that the teams at Zenseact are currently developing. But before we get started, what do you think is the best algorithm available to drive a car? Yeah, humans are good at driving cars, right? And what do you find? What is the algorithm? I think it is an end-to-end deep neural network that it's end-to-end in the sense that it takes sensory data as input and it outputs the next driving command. So we see biological versions of such deep neural networks driving cars every day. At Zenseact, we are trying to develop artificial deep neural networks to do the same thing. Although these networks, biological or artificial, can drive cars really well, it is hard to prove that the way they drive is safe. If you think about humans, if you have a new individual here, turned 18, how would you know that this guy or girl will actually be driving a car safely? How can you prove that? How can we trust this? I think what we humans do is that we look at historical driving data and we see that, yeah, you know, humans, if they follow the traffic rules and they are attentive to the driving task and they're not under the influence of alcohol, they should be sufficiently safe. Let's also do a short test, driving test, and if he or she passes it, off you go. You can drive your car. For artificial neural networks, we don't have such a process. And this is why we are equipping the end-to-end driving stack with safety guardrails. This talk is actually not so much about this architectural construction. It is rather a story of what Zenseact is developing and how we are developing it. And it is purely focusing on the deep learning parts, being at an AI conference. Since data is key, a lot of this talk will be about data and data pipelines. And you will see that deep learning and AI enters the story in the data pipeline as well. And then I will get into the in-car deep learning model, which will be the second part of my talk. And hopefully I will provide you with some entertaining videos and examples of this network. But before all of that, let's start with some context. Let's talk about OnePilot. This is a driver assistance system that we at Zenseact developed together with Volvo Cars. It can automatically drive the car as long as a human is supervising the driving. It can also avoid collisions autonomously, and it can provide information, for example, about speed limits to the driver. Zenseact is responsible for the software parts of OnePilot. But let's talk about the hardware part first, because this is really important. So the external system of OnePilot, slightly simplified, it has between 5 to 9 different cameras providing a surround view of the car. And why it's a range of cameras, it depends on which configuration of car we're talking about. It also has surround radars, 5 of them, ultrasonic sensors, and maps. All of this data is being streamed to a central computer in the car, which is powered by a system on chip from NVIDIA. And this is where we deploy all our software. The first generation of OnePilot is already in production. You find it, for example, in Polestar 3 and various Volvo Cars models. And the software architecture of the first generation of OnePilot followed, let's say, a traditional robotics paradigm, where sensory data is first you run detection. You try to detect all the objects in the scene. You do tracking over time, and you fuse information or detections from various sensors. You try to predict how the world will evolve. and then plan the next action of the car, and finally control the car. Let's see, do you see the colors here?
On the left and right.
This is interesting. Okay, so the detection box here is supposed to be yellow. And that is where we have deep learning in the first generation of OnePilot. The other boxes are blue, meaning that we're not using deep learning there. It's more classical methods, Kalman filters, and so on.
You can see the colors there on the...
Yeah, if you look on the left or, left or right screen, you can see the colors. Thanks, Rael. And here are some examples from this, from the deep neural networks that we developed. So here, each neural network consumes one image from one camera at the time. So it's frame-based. And we developed a full computer vision stack. Here are examples of object detection, free space and road detection, road edge detection, as well as holistic path. But there is a lot of more functions underneath the hood with camera calibration, blockage detection, visual odometry, etc. The holistic path is interesting. This is where the network is trying to predict where the car should drive. But since it only has access to one image, it has no understanding of how fast things move. If there is an object in front of the car, this network cannot know if the car is moving, so we should follow it, or if it is standing still, so we should brake. So this is why we call this a path. It's not a trajectory. In the second generation of deep learning, so this is what we commonly refer to as DL2 in the company, we wanted to elevate holistic path to holistic trajectories, the end-to-end trajectories. And that changes everything. So now we want to do the end-to-end trajectories as well as sensor fusion and object detection and tracking and prediction. All of this in one big, deep neural network. So we have to work not with images, but video streams, radar data, and so on. The enabling thing for this shift is that Volvo Cars and Polestar is updating the central computer to host not a Xavier chip, but an Orin X chip with much more compute available to do deep learning inference. And if we zoom in slightly more on this, so the yellow box here, if you look on the right screen, you see what's yellow, is called DL2. The details of this I will go into in the second part of my talk. But it is consuming all these surround cameras and the surround radars. And it generally basically outputs two sorts of outputs. One being the perception outputs, like objects, lane lines, and so on. And the other being the end-to-end trajectories. The perception output goes into classical trajectory planning. And the end-to-end trajectory then goes into a trajectory selector that compares the classical trajectory to the end-to-end trajectory. And we can, with the classical trajectory planning, we can provide boundaries within which it's okay for the deep neural network to suggest trajectories. And only if the end-to-end trajectory falls within these boundaries, we will let them through. So this construction is what we call the safety guardrails. Now you could have an equally interesting 40 minutes talk just on this safety guardrails, but that is not my talk. My talk is about the yellow box, the DL2 network, and how we develop that. So then let's talk about learning. The perception output, just as in DL1, we use supervised learning to train that. So we need lots of data with annotations. This turns out to be quite tricky to generate when it's sequences rather than images. For the trajectories, we are using imitation learning. So the network is trained to imitate what the expert driver or the driver who drove the car actually did. Very similar to how you train large language models. In the pre-training phase of large language models, they are given a sequence of words or tokens, and they're tasked to predict the next token. And in order to do that, you actually need to understand both language and have knowledge about the world. And then in large language models, they do reinforcement learning from human feedback in order to tune these models and behave in ways that humans prefer. And we are investigating doing the same thing for these end-to-end trajectories. But the bulk of what we do is imitation learning. Okay, so that was the kind of introduction. So let's go into how we develop these things. And step number 1 is to build a huge data set of training data. We need it to be of high quality. We need it to be of high diversity, because neural networks, as with any statistical method, are quite good at interpolating, but not very good at extrapolating. So we need to span the whole space of everything interesting that can happen. And we need to provide ground truth trajectories for imitation learning, and ground truth annotations for the objects and road and stuff like that. This, we really realized like a while back that this is a very hard problem, because DL2 puts very high requirements on quality, diversity, and the ground truth. So when we did the reorganization, we actually have decided to have a whole art or division solely purposed to generate beautiful data sets. And I see quite a few of you in the audience today, and I'm super happy and a little bit nervous to talk about the work that you do. Hopefully I'll get it right. So let's dive into it. In DL1, the training samples was an image from a camera. The size of such an image is approximately 5 megabytes. It is not too difficult to annotate it manually. You just draw boxes or lines in an image. We have done that. We have millions of such training images. But when you go to DL2, we needed videos and radar sequences. Typically like 10-second snippets would be one training sample. And if you have about 7 cameras on the car, and each of camera is providing data at 15 frames per second, just one training sample becomes approximately 2,000 times bigger than what we had in DL1. If you want to build a big data set, as we want, this becomes very expensive just to store it. Any operation you want to do with it more or less requires a GPU farm to do the processing. So it becomes slow, cumbersome, prone to errors, and expensive. When we looked into our data set that we had collected for DL1, and we tried to see, okay, how much of this can we actually use now to get started with the POC on DL2? I think the number was, I don't know, any guesses, by the way? It's an order of magnitude of 1 to 100 kind of samples, because we were super picky with quality. We needed to know exactly the calibrations, all the timestamps, no missing frames. Yeah, a bunch of stuff, basically. So quality was one thing we needed to address immediately. The next thing is annotations. So if you have a timestamp, you fire 7 cameras, and you annotate boxes in one of them, then you have all the other cameras. There is no way to reuse the annotations you did in one, so you basically have to do it in every camera, and then at every time step. So we're like, okay, this will not fly. We should go directly to 3D. All the sensors around the car can agree on what 3D is. There is a world around the car. So let's annotate boxes and lane lines directly in 3D. But we still have this time, the sequence with 150 time steps in one sequence. So when we did the math and looking into like what would it take to annotate hundreds of thousands or even millions of such sequences, it would take a long, long time for a human to do this. And it would cost a lot of money. So we took the strategic bet to invest in automated annotations. We call that pseudo-annotations. And we decided to develop a foundation model in this data art. A foundation model to assist us with the annotations. So here is a sneak peek to the data pipeline that we use to go from data, collected data, all the way to trained foundation model. So I will go through this and provide some examples. And after that, we will go into the DL2 model that we actually run in the car. Oh, we can go back one second. So the first row here, called data center, this is a shared data center with Volvo Cars. It can host like 100 petabytes of data. It has a massive CPU farm and a big GPU farm as well that we can use for all the processing. And then in the second row, we go to the DGX cluster. This is an on-prem GPU farm that Zenseact owns. And this is where we can train neural networks. Let's focus on the top row first. So step one is to collect data using dedicated data collection vehicles or probing data from the fleet. Whichever way the data comes, we ingest it to this data center. And then we run these quality checks that I was mentioning before, that our data collected for DL1 wasn't really up to par for the requirements we have for DL2. So actually this blue circle consists of 6 different stages where we check for various things. And anything which is not of high quality, we delete it. But it's not that easy. Because it turns out that the things that didn't pass the quality checks, quite often you could fix that with software. So we have kind of a healing process for data as well. So these 7 stages, I will just mention them like that, but it's a lot of work going in here, a lot of dedicated teams and a lot of automation. Then I also mentioned how big this data set was. 2,000 times, a sequence being 2,000 times bigger than an image. So it's very tempting to lossy compress all this image data to make it more lightweight. But if you have a background in computer vision, you will start to hear alarm bells ring if I say lossy compression. So we spent a lot of thinking and experimentation into this step, but finally decided to go for lossy compression. And then we can delete the raw files. Then comes offline post reconstruction. This sounds like difficult words, like what does it even mean if you're not in the automotive industry? But basically when the car is driving around and we collect data, we need to know exactly how the car drove. X, Y, Z, T, the trajectory it drove. This is absolutely crucial if you want to do DL2. There are various ways to understand this. Like if we want to do imitation learning, provide the neural network with some historic data and ask it to predict where to drive, the ground truth is how the driver drove the car. So we need to know exactly how it drove. And if we annotate 3D boxes for all the objects around the car at different timestamps, we need to be able to correlate them between the different timestamps. So then we also need to know exactly how the ego car drove. And finally, and maybe most importantly, for the foundation model that will do pseudo-annotations, we already have the full sequence available. There is no point in running it one step at a time. What if we can just aggregate all the LiDAR scans, for example, from our ground truth LiDARs into just one coherent point cloud? Then we also need to know exactly where the car was when each LiDAR sweep was done. And offline post-reconstruction is not an easy problem. Using very advanced optical gyroscopes from a very expensive box, let's say, that you can buy. If we use that inertial odometry estimations and aggregate point clouds from a few seconds, you get the image to the left. It's not bad. It's okay. But if you use LiDAR-based reconstruction, like LiDAR SLAM, you start to see that this improves the odometry quite much and the post-reconstruction. Here's another example. And every centimeter that we improve this accuracy directly translates to better annotations for the DL2 model, and thus a better DL2 model. When we started sending data to annotation companies, they were not super impressed by our offline post-reconstruction. Now we get to hear that we have the best post-reconstructions in the world. If we probe data from the cars in the fleet, many of them, or most of them, don't have LiDAR. So then we can do similar methods with camera-based reconstruction. This is a little bit more compute intensive. But in this particular example, we drove around on a parking lot for maybe 30 seconds. Using only the 4 fisheye cameras, we're able to reconstruct a point cloud like this. And then we can just once annotate all the parking spots and project them into each camera at any individual time step. So this is about aggregating data from many time steps into one coherent point cloud. Next, and the final step on the Odin data center, is to do curation. Like from all the data we collected, let's select the most interesting data points to train the neural network on. We want diversity rather than quantity. And here we use a lot of available foundation models from other companies. So we can query our database. For example, here we ask it, give me data or sequences from where pedestrians are crossing the street. And the way this works is that in this example, we're using the CLIP network from OpenAI. This is, for many people, a very known network, but I will still just say a few words about it. CLIP is trained on image caption pairs. So it has learned to take a sentence and embed it in a latent space where it can be compared to images. So if we run CLIP on keyframes in our data set and store those embeddings, then we can just search in text through our entire database, and in a matter of seconds we can get examples out. So this is super useful. And of course the teams have elaborated on that, combining with other foundation models like SAM2 and investigating vision GPA models and stuff like that to build ever more powerful methods to curate our data sets. Okay, so now we made it through the first line. Now we come to the foundation model. So the data has been checked for quality, lossy compressed, offline post-reconstructed, and curated. We chop it up in 10-second sequences and we extract it to our DGX data center. So now what remains is to provide annotations. And to provide the annotations, we can start with some manual annotations, but we cannot do too many. That just takes too much time and costs too much money. So instead, we want to train this foundation model that can do pseudo-annotations for us. But even that model will not be great if it only has access to a few manual annotations. So what to do? We pre-train it using self-supervision. And here's a tricky slide. I will not go through the details here, but basically the yellow box here that says LiDAR encoder, that's part of the foundation model. It can consume a history of point clouds, for example. And then we task it to predict occupancy in the future. Since we have the next point clouds available, we can calculate automatically the occupancy in the future. And we can train this network to predict occupancy. It's quite similar, right, to pre-training GPT or large language models predicting next token. In order to predict the occupancy or the next point cloud, the model has to understand how traffic works actually and how the sensor works. We can also task it to predict how the ego car will move. And then a very clever thing that we actually wrote a paper about and called GASP is that we can take the Dino foundation model from, I think it is Meta, since we have also cameras available in our data set, let's run Dyno on the cameras and then project the Dyno features onto the point cloud in 3D. And we can ask this model to predict Dyno features. Dyno features is like new release, if you wish, a latent representations of semantics. So now this model, when being pre-trained on massive amounts of data for weeks or even months, it learns something about traffic. And I asked the foundation model team to give me a video of the latest and greatest, and it turns out that the latest and greatest model is still in the cooking. So here it's been trained for like a week or two, and this is a representation of what it sees, looking into the latent representation of this model. So it can predict depth, and it can predict these Dyno features for this traffic scene that you see on the top. And we will continue to train this for a while. Of course, we have trained previous generations in the past. And after the pre-training phase, now we can just fine-tune it on quite a few manual annotations. And then we're ready to do the pseudo-annotation. Are you with me? So now we have a foundation model, and we want to do pseudo-annotations. And here are the results. So the colorful boxes now are the 3D detections of objects coming from our foundation model. And of course it has to work in highways, in cities, in rainy environments, where there's lots of objects around us, when there is fog, etc., etc., etc. And it does. It's actually awesome at detecting objects. This is a success story. We are also, or the teams are doing road annotations as well. This is a slightly harder problem actually. The model is getting really good. It's not as good as it is with objects yet, but it is still good. The green lines that you see here are what we call lane segments. The blue lines are lane delimiters, and the red lines are road edges. And you can see that it mostly does a very good job, but sometimes it's a little bit off. Now that's not the end of the world if it's a little bit off, because manual annotations and pseudo annotations is really a love story. Because if you start off with a few manual annotations, you use them to train your pseudo annotation model, you run your pseudo annotation model on new data, then you send that to an annotation company, or if you do it in-house, and you can correct the pseudo annotations. And now you can fine-tune it again on the extra data that you created and provide even better pseudo annotations. And you can traverse this loop as many times as you wish until you have a sufficiently powerful pseudo annotation model. And then you go on to a more tricky task, and you start again with the manual annotations, and you start this data flywheel. So we're not really replacing manual annotators, we're just leveraging them in a more clever way to get more bang for the buck. And we're extremely happy about the extremely fruitful collaboration we've had with our annotation suppliers on this, and I want to particularly mention Cognic in Gothenburg. This brings us to the DL2 model. So we basically want to do the same thing as we did with the foundation model, right? Detect objects and road, and of course do the end-to-end trajectories. But this time the model needs to run in real time. We have imperfect poses or ego motion, imperfect sensor calibrations, a very limited size of the model since it needs to be deployable on the SOC. And we have a lot of functional safety constraints to take into account as well, etc. Here is the architecture of the DL2 model. So starting from the left, you have the sensors, the surround cameras and the surround radars. Each sensor data is being encoded. For the cameras, we use CNN encoders, one image at a time, like in the DL1 days. And for the radars, we use point nets. out of the encoders come feature maps. So these are neural representations of the sensor data. And we fuse all of that in a scene builder in the middle here. This is really like the focal point of the network. It is a transformer architecture that is doing cross-attention to the feature maps. And then self-attention. And then cross-attention again. And then self-attention. As many times as you basically can fit on your SoC. And out of the scene builder comes a neural representation of the world around the car. And we want this representation to be as rich as possible. Of course, we humans don't understand it. It's just like numbers. But we can train heads, task heads, to cross-attend to this neural representation of the world to extract, for example, parking spots, objects, road, static objects, and the ego trajectories. You also see that I made these recurrent loops. So we want to make temporal fusion as well and tracking. And this is why we need some kind of mechanism to handle time as well. So the ego trajectories here at the bottom, they are really end-to-end in the sense that it's just one neural flow from input data to the trajectories, and we can back-propagate gradients all the way. This is why we call it end-to-end. We think that a trajectory is a good output representation of the next driving commands, but I will not go into all the details as to why. You could have imagined that the network would actually say exactly how much to brake or steer the car, but we think a trajectory is more useful. And on top of the ego trajectory, you have all these different perception tasks. Let's talk a little bit about what it takes to develop one particular detection task. Let's take the dynamic objects as an example. You need to understand the requirements and negotiate them with your stakeholders. You need to think about what data that is needed and the diversity of data and all the situations you need to create data from. You need to decide how to annotate this data. You need to design your head, which is also then a transformer. You need to take part in training the network and then get feedback from your stakeholders and see where to improve. And we have decided to organize ourselves with strong teams for each of these boxes. So there is 1 or 2 teams that owns each of these boxes. But then we don't want the different teams to go and invent completely different solutions. At the end of the day, this is one big neural network trained jointly. So therefore, we have a design guild with a representative from each team that meets and makes sure that this becomes a coherent design. Also, when it comes to data, we want to be efficient in the way we work with data. So we have a data guild with one representative from each of these teams. And in order to make sure that the way we train the model and follow up on KPIs, etc., we have a whole MLOps process. So starting from the annotated data that we have, we do what we call fine-grained curation. This is where we select, okay, which are the most important training samples that we want to use to train the network. We can use all these clip queries that I talked about, but now we can also use the annotations in order to study what scenarios are most interesting. And then we have this design phase and training phase, where we use the DGX machines. We want to train a new model approximately every 5th day from scratch. Or actually not quite from scratch, we do some pre-training. But anyways, a new model every 5th day. And then as soon as the model is done, we automatically generate a large number of KPIs. Some are high level, so that me and other managers can look at them and see, did things go up or down? And a lot of details, so the team can dive into the nitty-gritty details. And if we're happy with this model, then we deploy it, meaning that we need to take the OwnNX file that describes the entire network and all the weights and optimize it for the NVIDIA SoC. This is a crucial step because we want to build as big a network as possible, but run it at 15 Hertz on the SoC. So we have a whole team that is just masters at deploying neural networks and optimizing them, doing quantization where needed, pruning where needed, and so on. And we're using TensorRT also as a tool from NVIDIA in this. I also want to mention another Gothenburg company. We have had a lot of good collaboration with Embeddle in this space too. When the model is deployed, this is an automated step, but we constantly work on improving this optimization step. But it's still an automated flow here. It goes to our monorepo, where all the other product code resides. We call it the source repo, where we have a very powerful CI machinery. So now the network needs to pass all the gating tests and be integrated in the rest of the stack. And when that is done, we can test it. First in simulation, open loop simulation on large amounts of data we have collected, or closed loop simulation that I might have a second to talk about at the end of this talk. And if the simulation results are also good, we go out and drive in car. And we typically traverse this loop like once every second week. So we spit out a new model every 5th day, but it takes a few days to make it through all these steps. And then sometimes we're not so happy with the models. I would say on average, we have a new model in car every 2nd week. And then we collect feedback, right, from all these different steps. We collect feedback, we see if we need to create other data or improve the model design. So now comes video time. Here are some examples. Here are the end-to-end trajectories. So at the bottom video, you see green is the output from the neural network, and the blue line is the ground truth. This is how the driver actually drove the car. On the graph to the left, we look at the world from the top. And again, the blue line is the ground truth, how the driver drove the car. And we see here that in this case, we output 6 or 7 different candidates out of the network. Because sometimes it's difficult for the network to know whether we want to drive to the left or right in an intersection. So we equip it with several guesses. And then we have a mechanism to select which one is the best guess, which becomes the green curve in the video. And here's another visualization where we see again the green line being the end-to-end trajectory. If you look really carefully, it has some blue bars in it. That's every next second. So the first blue bar is at 1 second, and then 2 seconds. We predict up to 5 seconds into the future. And the pink boxes are cars, yellow boxes are trucks, blue boxes are pedestrians. The same objects and the same trajectory is also shown in the top view, where the white dots are the radar detections. Remember, the radar detections are also an input to the network, together with all the surround images. So this is just a way to visualize the output of the network. And now, we don't just detect boxes, we also need to know, so what is this box? It's a car. Where is it moving? We need to know exactly where it is, its pose and orientation, its velocity, its acceleration. Everything is being predicted directly from the network, end to end. And here are some more examples on the diversity of scenes that this network is capable of handling. And more. Rain and snow. So that's objects and end-to-end trajectories. Let's look into road estimation as well. Again, we predict the lane segments, the lane delimiters, the road edges, and these funny yellowish tubes are uncertainty predictions out from the network. And again, we need diversity. This needs to work when we have low-standing sun, or when it's raining, or when it's fog. And I think we've come a very long way. We're out testing in cars every day. We're hoping to deploy this into production as soon as possible. And this marks the end of my No. Final video, we have to show this. When you put it all together, and we go a testing car, then we can drive like this. And here is a mix of driving end-to-end and using the guardrails. So really excited to bring this into the hands of customers as the second generation of One Pilot. Zenseact, all about teams doing very cool things together. And we are hiring deep learning talents. Thank you.
Thank you so much, Erik. Super interesting. We have about 2 million questions for you.
Yeah.
We won't be able to cover them all, I'm afraid, but let's try and pick up a couple at least. The first one, of course, you've heard this one before, I think. How many years are we from fully autonomous cars?
Yeah. I mean, they do exist in limited environments already in the US.
And in Sweden?
Yeah, I don't know.
Okay. You mentioned this yourself in your talk. There's a lot of computing power and storage needed in real time to achieve this. Do you see that this is like a hurdle or an issue to scale up?
I mean, yeah, the computing power available in the car is one of the dimensioning numbers, I would say, or parameters in this game. But you also need to have a cost-efficient solution that provides the value customers are willing to pay.
Yeah.
I think working with the RNX SOC as we are doing today it's quite nice actually. It enables us to do very cool things. But we always spend a lot of time optimizing the networks to be able to do them big as possible.
Yeah. Do you see any other hurdles in scaling up?
I think everything is hard. So
yeah, that's true.
We have hurdles is all I see every day. I don't know.
Yeah. So what's the main...
I don't see any showstoppers.
Good. Good. What's the main reason that you discard data, and how do you make sure that conditions that lead to discarded data are not actually interesting in themselves? For example, if you discard data because the weather is bad.
Yeah, so I would say that typically we would not discard data because the weather is bad or if a sensor is blocked, because anything that can happen in real life is what we need to train the model to handle. But we also need fail-safe mechanisms to understand that now the conditions are sufficiently bad that we cannot trust the outputs of this network. So then we train networks on the bad data to be able to detect that now we have bad data.
Yeah.
But we want to get rid of repeating patterns, like trailing a white car on a highway. We've seen too much of that.
Yeah. Okay. Here's another one. I think you've heard this one before as well. How do you compete with Tesla when they have many years lead on data collection?
I think Tesla is super fascinating. I think it's great that they are around, paving the way, showing what can be done, moving the frontier. It's stimulating.
Good.
We just have to make sure that our stuff is very good and safe. We are all about safety.
Good. Other than mostly building large data sets and training, what does Zenseact do scientifically differently to tackle these problems? Could we get 1 or 2 solid examples?
So we have like 8 or 10 deep learning oriented PhD students at Zenseact, and they are publishing at the very best conferences in the world. We have invested a lot of focus on neural simulation actually, that I didn't have time to talk about, unfortunately, because I dragged on too long on the data. But definitely simulation, and that is very important. Yeah.
Yeah, good. I'm reading, there's new questions popping in all the time. I'm reading them as we speak, but maybe we have time for one more. How do you make predictions if a conflict or collision is more like much rare samples in the data sets we had. No, sorry, that was.
Yeah, but I think it is a great question. I mean, in general, the things that really matters for safety happens quite rarely in the data. So that is one of the tricky things. Class imbalance in general. That is why data curation is so important.
Yeah, good.
So there is no easy answer to that. That is a problem, but it is a problem in the sense that it is solvable.
Yeah. Okay. Good. Thank you very much. Give Erik a big applause. And of course, so you have a green T-shirt.
Yeah.
You need a matching umbrella, obviously.
Oh yeah, that would be great. And don't ask me for the way to the coffee machine or anything,
No.
because I don't know that.
Are you superstitious?
No, I don't think so.
I talked to my colleague Danila, who is in the main hall, and I said, you know, when we hand these over, we should open them because so everybody can see how nice they look. And she said, "Oh no."
Okay,
I'm
then it will start to
superstitious.
rain.
We can't do that because that's when it starts to rain.
Okay, then I will keep it folded. Thank you very much.
Thank you. Thank you, Erik.